Swayam Prabha. Digital India. Educated India.
Because the particles are joined together, so it's
Okay, so let us see whatever you are thinking, whether it is correct or not. So as she said in this slide, the left one is bulk material. Bulk means it is larger size, some thousands of nanometers. You can still write that as thousands of nanometers, but it is much bigger than the one which is on the right side there. Okay, few nanometers. The left one has a golden color, as your friend said. The right one, the color is different. In this case, in this particular case, in the base of gold, you will see that there is a change in color when you make it into smaller and smaller and smaller particle. Okay, so there is something happening at that level. So we have to see what is happening and what are the nanomaterials. Not every material which you can specify into nanometer length scale is a nanomaterial. It's mostly between a dimension, that is 1 to 100 nanometer. And why the dimension of 1 to 100 nanometer is important is what we need to find out. Okay. So as I said earlier, many things, nanometers existed before. We could not see the initial optical microscope images which you could magnify. Could be only 1000 to 1500 magnification. And then you can also now go to electron microscopes. So in the previous case, you use, what do you use? What is the probing mechanism here in optical microscope? Light, visible light. You use visible light to probe something which is under an optical microscope. That is why the word optical. Electron microscopes, you use electrons. You use electron beam to investigate that. But why is it that you use electron microscope here, and how can you see at that level? You see the resolution is around 1/20th of a nanometer. It's very small scale. So why do you need electron in this case to go down to that level? Extremely small. So all the waves, the waves corresponding to these electrons have almost of the same order dimension as that of the microstructures which we see here. So normally, simply put, if you want to measure the length of a notebook, you use a normal ruler. But if you want to use measure the dimension of this room, you can't use your ruler. What do you use in that case? An inch tape or something. So the object which is under under investigation has to be, or the probing ray has to be of the same dimension, almost of the same order as that of the object which is being probed. So that's why when you want to go down to that level, you need electron microscopes which have a higher energy as compared to that of the optical waves which you used initially. Okay. Okay. So we'll go through some pictorial quiz now. What is that image which you see here? Left hand side? These are images which have been taken using an optical microscope. So it's not a very high magnification. Left hand side, these are pollen grains. Okay. Right hand side, what you have is a light bulb filament. Okay. What about this? You can guess. If you have taken, any of you have bio, this is a cross section of a leaf. Okay. So these are something which you can easily see under optical microscope. What about this? Fungus, bread mold, yeast. Why are you giving me examples of only biosamples? Amazon forest. You need to see Amazon forest using microscope? No. So this is an organic microstructure grown using copper oxide. Okay? But this is again something which you can see under optical microscope. Next is something where you need a higher magnification probe. What is this? Eye of a fly. Okay? So you see these structures existed much before us, but we couldn't see any of these. What is that? What does it look like? Fiber? Any of you have seen this before? You don't need to see this. Okay? Okay. So, yes, so now we are going down, we are magnifying our view, and you can go down to this level where you can see atoms. Okay, this is a STEM image which is called a scanning tunneling electron microscope, which is again a specialized form of electron microscope where you can go down and see the atoms as well. Okay. So what I want to say from this is we have had nanomaterials in nature. We have also had nanomaterials which was already there. Only thing is we could not see it. Okay. Now the dimension which we were discussing now. So the right one is a RBC. Okay, and that also, you can. I think this is hidden. You can write this dimension in nanometers. Even a human hair is about 1000 nanometer thick, but this is not a nanomaterial. Okay, so even though we have had nanomaterials which are naturally occurring, even in the ashes of a volcano, you will see nanomaterials there. And there are man-made or engineered nanomaterials or functional nanomaterials which we use for different applications. Okay, so they are also called incidental or engineered nanomaterials, where you use them for specific applications, like we have seen before in the application of functional materials. Now the difference between incidental and engineered is, incidental you don't have a control on the morphology or the uniformity of the particles, whereas in case of engineered ones, depending on your application, you can engineer the size, shape, and even the uniformity. Okay. So as I was mentioning before, normally between 1 to 100 nanometers thickness materials are defined as nanomaterials, but it's not just this dimension. There is something else which plays a very important role. If you take the example of a normal cube, okay, and you measure its surface area and volume. What is the surface area of a cube? Volume. So if you take a surface area to volume ratio, you will get some number there. Now divide the same cube into 4 equal cubes and then further into 16 equal cubes, and then try to measure the volume and the surface area. What you see is a drastic change in surface area to volume ratio. And if you keep on cutting down this cube into smaller and smaller cubes, there will be a stage where the area of that cube can also be equal to the area of a football ground. So the point which I want to tell you is, the surface area to volume ratio for a nanomaterial is very high as compared to that of a bulk cube, the first case which you see here. Okay. So why does the size matter? Because when you go down, when you take a bulk case, that means this side, when its size is big, okay, much more than 100 nanometers, which we are discussing about, at the macro scale, most of the atoms which are there is in the bulk of the material, that means inside the material. And very few of these atoms are on the surface. So when these atoms are on the surface, what happens is you have what are called dangling bonds. The word dangling itself suggests that they are hanging. They don't have any friend with them. Because, but on the other hand, the ones which are inside, they are fully occupied. No hands are free. Okay, so all their bonds are occupied inside. But the ones on the surface have one or two bonds which are still unoccupied. They can, so what happens if your next seat is free? The next person coming can come and sit there. But if it's not free, they have to look into some other place and make themselves comfortable there. So the point is, when you have large amount of materials inside and very small number of atoms outside, the dangling bonds are much lower here. Whereas when you go to nanoscale, since we saw in the previous slide, the surface area to volume ratio is very high. That means the amount of surface atoms or the dangling bonds is much higher in case of nanomaterials than compared to that of the bulk material. Okay. So what happens if that is the case? Just like I said, if the space is empty, somebody can come and sit. The materials or the atoms which are at the surface, they can react with any neighboring atom or ion whichever comes next to that. So the reactivity, that means the dangling, because of the presence of dangling scale, the reactivity increases. They can interact with at a much larger scale as compared to the bulk counterpart. So if you take bulk gold and you take a nano gold, the reactivity of nano gold will be much higher than that of the bulk. Okay. Other than that, there are other effects. So depending on which material you use, what size you have gone down, there are many other effects which come into play, and one of them is a quantum size effect, where as you go on decreasing the size, what you see is the energy levels. So initially we were discussing about continuous conduction band, very close conduction band which is composed of very closely lying energy levels. But when you go down, that is for a bulk semiconductor. When you keep on decreasing the size, these closely spaced energy levels now actually become discrete levels. And electrons can only occupy those discrete levels, or they can only have those energy levels. Okay, so when this discreteness happens, we call it as a quantum size effect. And this quantum size effect and also the higher reactivity normally happens only between 1 and 100 nanometer. That is why that length scale is important. So for quite a large number of materials, when the size is between 1 to 100 nanometer, you see these changes. Okay, that is why this is very important. The scale is very important. So when you change the size, you can have n number of properties depending on which material you are taking. You can have modified electrical properties, magnetic, mechanical, catalytic, which we are interested in. All these changes, because the higher surface to volume ratio comes into effect. In some cases, mostly optical, the quantum size effect plays a role. So because of the size dependent property, you can apply them there. You can use them for various applications like energy, catalysis, textiles, medicine, and various other areas. One of the most important is textiles, which is a very fine example of how you can engineer a material. Okay, engineering material, we have seen that you are designing a material for a specific application. So what do here? You create nanostructures on the surface. So basically the roughness is in the size of nanometers. So what happens is the contact angle between water or dust and the surface is changes drastically, just like in the case of a lotus leaf. So if you magnify a lotus leaf, you will see that there are surface corrugations which are of that nature and that size, which makes it hydrophobic. Okay, so similarly you can design your coating and make it, so design the surface or the roughness such that it becomes hydrophobic. So you can have water resistant textiles, you can have dust free textiles. So hydrophobic coatings are used very often in clothes to help them keep stain free. So other than that, we have already seen what is photocatalysis. When you have photocatalytic material, you can, I'll give you an example here. So this one, you see, when you have a material, this is calcium ferrite, which is in bulk size. Bulk size means it's not a nanomaterial. So it degrades in 6 hours. That means if you take methylene blue, it will break it down in 6 hours under sunlight. Whereas if you take a nanostructured CFO, the same material but synthesized in nano form, it takes just 15 minutes to degrade. So since the surface area is very high, the reactivity is very high, it reacts with the pollutant and breaks it down much faster as compared to that of the bulk material. It's a very simple example of what we know about nanomaterials. This is another example where you see the role of nanostructured CFO as compared to bulk. So when it is in a bulk form, that is the size is much higher. CFO is actually, if you see this brown, this is called the XRD pattern. So it will tell you that this is calcium ferrite. This is bulk calcium ferrite. It is dark in color. But if you make it into a nano form, there are various ways of synthesis to make it into nano form. You see the color, it's different here. Okay. Now, when you keep it under ambient conditions, after some time you will see that the color of this nanostructured one keeps changing, whereas the bulk one doesn't change. What happens in the case of nanostructured one? Because of its high reactivity, it starts reacting with CO2 at room temperature and starts converting into, so if you write down the reaction, you will see calcium carbonate and iron oxide as the byproduct. So calcium carbonate, there are various ways to know what are the things which are forming, XRD, 10 and all those. But the brown color actually comes because you have iron oxide forming there. Another interesting thing is when you heat this, it will come back to its initial form because it gives away CO2 again. So this is a very important material for carbon dioxide capture at room temperature. And if you see the reactivity with compared to bulk, okay, bulk CFO, there is no activity almost, whereas nano one, you see the carbon dioxide capture capacity is very high as compared to that of bulk, and it can also be recycled to a number of cycles as compared to that of bulk. So these are something which examples which tells you the importance of synthesizing a material in nano form. Similarly, photoactive materials, as I just said, can be synthesized in nano form, and you will see very enhanced activity in case of nanomaterials. Okay, and how can a nanomaterial be formed? This is I think almost the last but second slide. You can have two methods of synthesizing nanomaterials. You start from gold bar and come to a nanomaterial. That is called the top-down technique of synthesizing nanomaterial. You have several examples. Lithography, if you have heard, for etching and in milling, quantum well lasers, etc. Okay, we are not going into details, but you can be aware of what are possible synthesis techniques. Bottom up is something where you have atom by atom assembly or arrangement of atoms, and you start from bottom and go all the way to a nanomaterial, starting from one single atom. Okay, that is called the bottom-up technique, and you can have various methods like vapor depositions. Most of the chemical techniques which are present are the bottom-up techniques because you start from the atomic level or ionic level. Okay. Okay, so these are various interesting morphologies which are possible for a nanomaterial. This is that of a TiO2 nanostructure. This is from a journal. You see the various forms it can be produced, and all of them will have different morphology, interesting, different electronic structure. It may also have a different reactivity. So these are all functional materials where you can design them as per your choice and application. Okay, so we'll stop with this. And I will just show you one video which is a gist of, this is from YouTube, but it tells you why a nanomaterial is important. So what you see here is, you have a cube, the same example what I showed you, and you break it into, find out the surface area, break it into a number of smaller cubes. You will see that the surface atoms, the violet ones here are the surface atoms, and the red ones are the bulk atoms which are inside. They are all packed, but the surface atoms have free ends which can react. So if you take a cube again of 10 centimeter and then shrink it and press it down such that you have a surface area to volume ratio, you can calculate for this 0.001 centimeter. It's the same volume. Volume is not changing, remember. Even in the previous case of cube, volume doesn't change. It's the surface area alone which changes. You see the change in surface area? It's 2000 centimeter inverse now. Okay, the surface to volume ratio. And when all the dimensions are in the same range, 1 nanometer, you will have a very large increase in surface area. So these are various carbon allotropes which are there, which are nanomaterials, and they have a very high surface area. Okay. Okay, so I will stop with this. I hope you will remember something after this class. If you have any more questions, I am ready to take. Okay. Let us ask.
You told about trap states or defect states, right now. Those are the states with similar energy levels, right now.
Trap states are the defect states. So defect states, what I said is, these are, so normally in forbidden energy, that means if you have conduction band in a semiconductor, when you have conduction band and you have a valence band, there is a region in between where there are no energy levels. That means electrons cannot have energy in those that region, that is called the forbidden energy gap. But due to the synthesis or various other conditions like doping or adding impurity, you can have certain energy levels which come into effect and they fall in that region. Even though it's forbidden, they fall in those regions. So those corresponding to those defects, we have what is called a defect energy state. If you have charges, electrons, holes, they sometimes tend to go to that level and stay there for some time. So when they are staying there, they cannot participate in reaction. That's why we call them a trap state. And all these trap states have certain lifetime. Okay. So if the lifetime is more, that means the electron stays there for longer time. It doesn't want to come out and it doesn't participate. Okay. Yes.
Ma'am, I have a doubt. Like you said, nanomaterials are usually synthesized by either like cutting down the bulk materials or like building up from the basic levels. Like suppose hypothetically we like shrink the bulk materials and form a nanomaterial. Will the properties like still change or will it like remain the same as a bulk material?
It will change. No, shrinking is what we did just now in the video which you saw just now, it was shrinking. There was no cutting down. But you have shrunk the same volume into all the 3 dimensions. So even if one of the dimensions is in between 1 to 100 nanometers, the properties can change. If you shrunk that material along all the 3 dimensions, the property will change even more. Okay, the volume in the materials which we have discussed, the volume remains the shrinking means you have the same volume, but you are changing the surface area alone, pressing it into a flat. If you take a cube, press it into a flat plane, it's shrinking. You are shrinking it along one dimension. Even then the volume, because the surface area will change.
What about like chemical properties, ma'am? Like
chemical properties are the ones which change mostly because the dangling bonds are there. They become more reactive. Okay. It depends on how much you have shrinked it. If you have shrinked it to very low level, you will be able to see quantum size effect. If it is little above that, you will see a change in reactivity. Okay. So depending on how much you have shrunk, the properties will change. But obviously, it has to be within certain dimensions, and this 1 to 100 nanometer is different for different materials. It's not that for this material also the nanomaterial properties will change within 1 to 100. For this it may change within 1 to 10 only. If it's 80, it may not change. So it depends on which material. So 1 to 100 is kept because most of the materials fall in this range. Only when the size is between this, one of the dimensions is between this, you see a change in properties of these materials. What is quantum size effect? So quantum size effect is again as you keep on decreasing the size, at a certain stage you will see, do you have a chalk here? So okay. So normally when you talk about semiconductors, this is a very small, simplistic representation of what is a conduction band. So you have continuous levels, closely spaced energy levels in what is called a conduction band and a valence band, and you have a forbidden energy gap. When you keep, this is for a bulk material. Okay, normally it's not like this. This is just in school books, but you will see this is what is a diagram. When you make it into smaller and smaller size, these closely spaced levels, which you called as a band, they separate out and they become discrete. So between any 2 levels itself, these are not equidistant. Okay, between any of these 2 levels itself, you see a space. So these are discrete levels. And that is because of this, the electronic properties change drastically. Okay, and actually, if you will see an absorption, if you could record optical absorption, you will see a change in the absorption. If it was absorbing in blue region, it may absorb in red region now, or vice versa. Okay, so the electronic levels change drastically as a result of this. Electronic and optical properties also change drastically. That is what is a quantum size effect. Okay. So by quantum means you are going down to a quantum level. Okay, very small level.
So you told us about.
I think I will take one more question. How much time do I have? That's what, one more, because we will have other. Yeah, tell me.
Yes, ma'am. Ma'am, so you told us that when an electron is taken away from its particular spot, there's that hole being formed, right? So
hole is not formed. Hole is nothing but absence of electron.
Yes, ma'am.
Okay, so for example, if you have electron here, okay, it moves to this. Now there's no electron, and now this we call it as a hole. Similarly, if it moves from here to here, there is a hole here. Okay, so it is absence of electron. When electron moves here, hole is supposed to move in an opposite direction. Okay, this is a simplistic representation of what is a hole.
Ma'am, so I'm not able to understand how the hole reacts with water and converts the hydroxyl radical to the ion.
So basically, absence of electrons means your energy level locally is different. Okay, so in that case, that molecule will react with water at a different energetic. The kinetics are different. So it forms hydroxyl radicals, whereas electrons, it will go and reduce something, it forms something else. Here there is absence of electrons. So the energy there is different compared to what you see in an electron and oxygen reaction. Okay? Okay, so thank you very much. I will leave my email ID with Professor Venkat or Mr. Palni. If you are interested, you can write to me. Okay, and the slides, except few slides which are research slides, I'll try to share it with Professor Venkat, and if you want to have it, you can have it, no problem.
Ma'am, first of all, I'd like to thank you for taking time out of your busy schedule and coming here to give us an insight on functional materials for energy and environmental remediation. I'm sure everyone enjoyed your lecture on photocatalysis and nanomaterials. So, on behalf of all the RSIC students, thank you very much, ma'am.
Thank you. Thanks a lot. I'm happy that it was a very interactive crowd, and I hope at least 50% of you were not sleeping.